Hello everyone, I'm Rudra Mukherjee, a postdoctoral researcher in Bendable Electronics and Sensing Technologies Group, University of Glasgow. I'm going to present my paper on life cycle assessment of energy generating flexible electronic skin. Flexible electronic skins with various kinds of sensors have been used in different applications like wearables, prosthetics, and robotics. One important aspect is the energy autonomy of the skin. It is important to ensure continuous operation of its sensors and the related readout electronics. In this direction, recently our group has demonstrated a solar e-skin consisting of an array of miniaturized solar cells. In addition to energy harvesting, the solar skin can act as a proximity sensor without any additional electronics. Such energy autonomous e-skins are expected to find large-scale applications in various fields. Such large-scale applications can add to the already enormous volumes of electronic waste. Hence, it is important to assess the life cycle of each component of the solar skin and identify potential green alternatives. Following are the relevant elements of the life cycle assessment of the solar skin, starting with the fabrication costs. It includes the cost of raw materials for substrates, photoactive materials, and electrodes, and the materials required to integrate the solar cells to the skin, like wiring and sealants. An immediate cost involved is the disposal of byproducts, excess solvents, and materials used during the fabrication. Usage of any kind of biohazardous material during the fabrication process adds to this cost considerably. Once the cells are integrated on the skin and installed on site, there is a cost recovery in terms of the monetary value of the energy generated by the skin. The next element is the disposal cost. Once the skin starts to degrade, either due to mechanical abrasion of the substrate or decrease in the efficiency of the cells, firstly, the wires and encasings must be separated from the skin, followed by detaching the solar cells and other electronics from the skin substrate. Most of the substrates themselves can be directly composted. Some part of the waste materials from the solar cells can be recycled, other parts need to be chemically treated. The biohazardous materials are disposed of by standardized methods, and the non-biohazardous materials are mostly used in landfills. The substrate used for the solar skin is polydimethyl siloxane, PDMS. It is one of the most used chemical in personal care products, detergents, foods, and medicines. PDMS films are flexible and stretchable and suits well as substrates for the e-skins. The preparation costs of PDMS films are about $140 per meter square. PDMS can be easily disposed of, they can be directly composted and do not show any bioaccumulation or phytotoxicity. On one side, accumulated PDMS waste can be incinerated, giving out silicon dioxide and carbon dioxide. The environmental friendly method is to compost it in soil or release in water. In approximately 1 to 4 weeks, 50% of the PDMS by weight hydrolyzes to dimethyl silane diol. Dimethyl silane diol itself is a volatile product. It either biodegrades to silicon dioxide, carbon dioxide, and water directly in soil or vaporizes to atmosphere, followed by photodegradation to the same end products. It can also undergo humidification and remain embedded in the soil. Coming to the other part of the solar skin, the silicon solar cells. The recycling of silicon cells is widely reported in literature. The fabrication cost of flexible silicon solar cells is about $79 per meter square. It requires stringent processing conditions and processing temperatures of about 800 to 1000 C. Various hazardous chemicals are used during the fabrication, for example, phosphine gas for end doping. Lead is used in sealants, etc. For sensory applications of these cells, each cell in the array has to be read individually. That adds to the quantity of the wires required. On an average, 20 centimeters of wires are required per cell, amounting to about $1.5 per 25 cells. This cost can be reduced by using other printed methods. The total disposal cost of such silicon cells is about $11.9 per meter square. In terms of cost recovery, monetary value of the generated energy is about $140 per meter square per year. So the choice of the optimum characteristics of the solar cells that can be used for the solar skin involves taking into account the recyclability, the end of life disposal costs, and the less usage of hazardous materials. Of course, the first criteria is the highest power output and lightweight. Materials like gallium arsenide, indium gallium phosphide provide the highest power output per meter square, but their manufacturing costs are much higher as compared to silicon cells. Additionally, they use materials like arsenic, cadmium, etc. that are highly biohazardous. One of the potent alternative is hybrid perovskite solar cells. They offer power output at par with silicon solar cells with much lower fabrication costs. They are directly 3D printable, making their integration with the skin much easier. One problem is that they use lead iodide as one of its constituents and carcinogenic solvents like DMF and DMSO during fabrication. But recent reports of high efficiency lead-free perovskite cells and usage of green solvents makes them a promising option for the solar skin. In terms of the substrate used for the solar skin, PDMS is one of the best options as it is biodegradable, highly flexible and stretchable, but it is not suitable for certain applications like in high temperature environments, greater than 80 to 100 C. Using other potential alternatives involve trade-offs like for example, EcoFlex can withstand higher temperatures but are not directly compostable. Polyurethane are 3D printable, tear resistant and resilient to chemical attacks but involve costly recycling processes. SBS, another 3D printable substrate, is optimum for very low temperature operations but have no direct recycling method. One of the best substrate is TerraTech Flex. It is directly compostable, 3D printable, highly stretchable and comparatively lightweight. In conclusion, firstly, in addition to the power density and specific power, the recyclability and biodegradability of the solar cells must be considered. The ideal choice involves a printable and compostable solar cell that can be readily integrated to the robot's body and can be disposed of without any pre-treatments. Secondly, considerable costs are involved in the disassembly and disposal of the silicon cells used in the solar skin. Perovskite and organic solar cells formed apt choices owing to their low cost, printability, and self-healing property. And lastly, the use of biohazardous materials during fabrication adds to the disposal costs. To ensure sustainability and bringing down the disposal costs, the fabrication processes must move towards green solvent and find potent alternatives for biohazardous elements like lead and arsenic that are currently used in solar modules. This work is supported by EPSRC and the European Commission through Marie Curie Innovative Training Network. Thank you.